Chapter 12 Magnetism. Exercises, pages 227, 288. Exercises, Q1, I, page 227. Choose the correct option. Let R be the distance of a point on the axis of a bar magnet from its center. The magnetic field at R is always proportional to. Solution. Let R be the distance of a point on the axis of a bar magnet from its center. The magnetic field at R is always proportional to 1. R3 exercises, Q1, E, page 227. Choose the correct option. Magnetic meridian is the plane 1, perpendicular to the magnetic axis of Earth 2, perpendicular to geographic axis of Earth 3, passing through the magnetic axis of Earth 4, passing through the geographic axis. Solution. Magnetic meridian is the plane passing through the magnetic axis of Earth. Exercises, Q1, E, page 227. Choose the correct option. The horizontal and vertical component of magnetic field of Earth are same at some place on the surface of Earth. The magnetic deep angle at this place will be 1, 30 degree 2, 45 degree 3, 0 degree 4, 90 degree. Solution. Exercises, Q1, if, page 228. Choose the correct option. Inside a bar magnet, the magnetic field lines 1, are not present, 2, are parallel to the cross-sectional area of the magnet, 3, are in the direction from N pole to S pole, 4, are in the direction from S pole to N pole. Solution. Inside a bar magnet, the magnetic field lines are in the direction from S pole to N pole. Exercises, Q1, V, page 228. Choose the correct option. A place where the vertical components of Earth's magnetic field is 0 has the angle of deep equal to 1, 0 degree 2, 45 degree 3, 60 degree 4, 90 degree. Solution. Exercises, Q1, V, page 228. Choose the correct option. A place where the horizontal component of Earth's magnetic field is 0 lies at 1, geographic equator, 2, geomagnetic equator, 3, one of the geographic poles, 4, one of the geomagnetic poles. Solution. A place where the horizontal component of Earth's magnetic field is 0 lies at one of the geomagnetic poles. Exercises, Q1, V, page 228. Choose the correct option. A magnetic needle kept non-parallel to the magnetic field in a non-uniform magnetic field experiences 1, a force but not a torque, 2, a torque but not a force, 3, both a force and a torque, 4, neither force nor a torque. Solution. Both a force and a torque. Exercises, Q2, I, page 228. Answer the following question in brief. What happens if a bar magnet is cut into two pieces transverse to its length, along its length? Solution. Exercises, Q2, E, page 228. Answer the following question in brief. What is the unit of magnetic intensity? Solution. C unit, Weber or Tesla. Exercises, Q2, E, page 228. Answer the following question in brief. What could be the equation for Gauss' law of magnetism if a monopole of pole strength P is enclosed by a surface? Solution. Exercises, Q3, I, page 228. Answer the following question in detail. Explain Gauss's law for magnetic fields. Solution. Current, I, carrying solenoid. Electric dipole, I. The areas, P and Q, are the cross-sections of three-dimensional closed Gaussian surfaces. The Gaussian surface, P, does not include poles, while the Gaussian surface, Q, includes the N pole of a bar magnet, solenoid, and the positive charge in case of an electric dipole. E. The number of lines of force entering the surface P is equal to the number of lines of force leaving the surface. This can be observed in all three cases. E. However, the Gaussian surface Q of the bar magnet encloses the north pole. As even a thin slice of a bar magnet will have both north and south poles associated with it, the number of lines of force entering the surface Q is equal to the number of lines of force leaving the surface. If, for an electric dipole, the field lines begin from a positive charge and end on a negative charge. For a closed surface Q, there is a net outward flux since it does include a net positive charge. V. Thus, according to Gauss' law of electrostatics. Exercises Q3, E, page 228. Answer the following question in detail. How does the magnetic declination vary with latitude? Where is it minimum? Solution. Magnetic declination varies with location and over time. As one moves away from the true north, the declination changes depending on the latitude as well as the longitude of the place. By convention, declination is positive when the magnetic north is east of true north, and negative when it is to the west. The decline is small in India. It is 0 degree 58 west at Mumbai and 0 degree 41 east at Delhi. Exercises. Q3. E. Page 228. Answer the following question in detail. Define the angle of deep. Solution. Angle made by the direction of the resultant magnetic field with the horizontal at a place is inclination or angle of deep, phi, at the place. Exercises. Q3. If. Page 228. Answer the following question in detail. What happens to the angle of deep as we move towards magnetic pole from magnetic equator? Solution. At the magnetic pole, value of phi equals 90 degrees and it goes on decreasing when we move towards equator such that at equator value of phi equals 0 degrees. Exercises. Q4. I. Page 228. Solve the following problem. A magnetic pole of a bar magnet with a pole strength of 100 am is 20 centimeters away from the center of a bar magnet. The bar magnet has a pole strength of 200 am and has a length of 5 centimeter. If the magnetic pole is on the axis of the bar magnet, find the force on the magnetic pole. Solution. Exercises. Q4. E. Page 288. Solve the following problem. A magnet makes an angle of 45 degrees with the horizontal in a plane making an angle of 30 degrees with the magnetic meridian. Find the true value of the deep angle at the place. Solution. Let the true value of deep be phi. When the magnet is kept 45 degrees aligned with declination 30 degrees, the horizontal component of Earth's magnetic field B equals BH cos 30 degree, whereas the vertical component remains unchanged. Exercises. Q4. E. Page 228. Solve the following problem. Two small and similar bar magnets have a magnetic dipole moment of 1.0 m2 each. They are kept in a plane in such a way that their axes are perpendicular to each other. A line drawn through the axis of one magnet passes through the center of other magnet. If the distance between their centers is 2 meters, find the magnitude of the magnetic field at the midpoint of the line joining their centers. Solution. Let P be the midpoint of the line joining the centers of two bars magnets. As shown in figure, P is at the axis of one bar magnet and at the equator of another bar magnet. Thus, the magnetic field on the axis of the first bar magnet at distance of 1 meter from the center will be. Exercises. Q4. If. Page 228. Answer the following question in detail. A circular magnet is made with its north pole at the center, separated from the surrounding circular south pole by an air gap. Draw the magnetic field lines in the gap. Solution. For a circular magnet. Exercises. Q4. If. Page 228. Answer the following question in detail. Draw a diagram to illustrate the magnetic lines of force between the south poles of two such magnets. Solution. For south poles of such circular magnets facing each other. For south poles of bar magnets facing each other. Exercises. Q4. V. Page 228. Answer the following question in detail. Two bars magnets are placed on a horizontal surface. Draw magnetic lines around them. Mark the position of any neutral points where there is no resultant magnetic field, on your diagram. Solution. The magnetic lines of force between two magnets will depend on their relative positions. Considering the magnets to be placed one beside the other as shown in the figure, the magnetic lines of force will be as shown.